Now I'm going to talk about the equalizer. So this is another categorical gadget. It's another universal construction. And I don't do it justice, although it's shown in the book in Sheaf Theory Through Examples and wonderfully featured in Eugenia Chang's Joy of Abstraction. I don't show the universal scaffolding that demonstrates the universal property here. But the equalizer is a universal construction with this sort of shape. Okay. So we have two objects, X and Y, and we have two morphisms. This can occur in a broad variety of categories. We'll have equalizers. Not all, just like not all categories have products, or not all categories have terminal objects. Not all categories have equalizers. Those are all examples of limits. But if you have an equalizer, it's of this form. So in a category, you have two objects, X and Y. You have two morphisms, F and G, going from X to Y. And an equalizer has the property that you further have an object E, which we might informally call the equalizer object, but the equalizer is this whole structure, such that this morphism E is such that you have this property F after E. So if you compose F and E, it's the same as G after E. And this has to uniquely factorize any other. So if there's another object F that claims to be the equalizer, it has to have unique morphism that has this shape. So it has a morphism to X with this property. There's a unique morphism. It's factorized by capital E here. There's a unique morphism to it. Now, at first glance, this looks perhaps inscrutable, but it turns out to be incredibly useful. One important thing to start to understand its utility is that E here, the morphism from capital E to X, E here, is a monomorphism, meaning it's like a sub-object of X. Okay. And so you could think of this as kind of being the subparts of X that are mapped to Y in the same way. The subpieces of X that F and G map to Y in the same way, that sort of are mapped onto the same destination in Y, that are sort of the subparts of X that F and G treat the same to each other. Now, that's a bit vague. Let's talk about it for set. Category set. Category set, E, capital E, X, and Y are all sets. F and G and little e are what? This is the category set. We have objects or sets, and morphisms are what? Functions. So F and G and E are functions. So what this is saying is that if you do morphism, if you do function E and then compose it with function F, so F applied to the results of E on this, you get the same thing as G applied to the results of E on a given E. But it's nice to think of E here, and this is quite true. Capital E is a subset of capital X. It is the subset which F where f of x, so it's a subset of little x with an x. So capital E is a set. And what are the elements of the set? Well, they're elements of x. That's why it's a subset of x. They're elements of x. But they're elements of x that are special, elements of x that are such that f of that element is equal to g of that element. That those are mapped to the same y. So if you hit them with x or with f rather, or you hit it with g, it's a subset of x such that if you hit it with f and you hit it with g, you get the same value of y. Are we okay with that? So maybe let's do a little example. This may seem abstract, but it's actually very, very sensible. Very, very sensible. So I'm going to, I think the easiest way to do this, I'm going to stop screen sharing here. I think the easiest way to do it is to show it something like this. So I'll have A, B, and C. Maybe I'll have 0 and 1 here. And let's suppose that A maps to 0, B maps to 1, and C maps to 0. This is X, and this is Y. And I'm asking here, what is E? E is some subset of these. It's some subset. So I hope you'll forgive me if I label the elements of E as just elements of this. And in fact, it'll be like pointing, it'll be, this is a monomorphism. What's the equivalent of a monomorphism in set? Does anyone remember? What sort of function is the equivalent of a monomorphism? No objects goes to the same thing. So what is it called? We call that a what function? Begins with I. Yeah. Injective function. It's an injective function. That's what a monomorphism is here. Okay. So if I take the equalizer, okay, so here we have one mapping. This is F, right? This is F. This is one mapping. And so we'll just remember F is red, and I'm going to need another color.
It's a black one.
Here. Okay, great. Thank you. Okay. Let's suppose that we have here A going to 1. It's kind of unsettling how if you really press hard, it like actually produces something. Let's suppose B goes to 1. Goes to 1. B goes to 1, and C goes to 0. Okay. 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 So these are two. So this will be G.
Yeah, the Y is on the table. Yeah.
Yeah.
But these are blue ones. Okay. I think everyone wants blue ones.
Yeah. 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 There we go. Okay. Okay. So we are looking for the subset of X that are what? That are mapped onto the same So that F and G agree as to where they map here, right? So what subset of X are mapped in the same way by F and G?
B and C.
B is mapped in both cases by the red and by the black, such as it is to 1. So F and G agree there. So B is in our equalizer set. That set of equalizers, which we might call equalizer of F and G. We might call this set. The equalizer is the whole construction thing. And Jeff, you said C. C is mapped by F to 0. C is mapped by G to 0 as well. So C. Why not A?
F and G take A to different elements of Y.
Exactly. It's mapped discordantly. A goes to 0 by F, and A goes to 1 by G. So this is the equalizer of F and G here. Are we okay with that? Okay. So maybe I'll ask another question. So let's suppose we had a set. And maybe I'll even do it with the same ones just for keep the bit on mine. Okay, here we go. And I'm going to have F just map everything in a constant way. So F maps everything to 0. And G maps A to 0, B to 1, and C to 0. What is the equalizer of these two functions?
Set of A and C.
Set of A and C. It's the set, it's a subset of this, set X. Label them again. Okay. The subset of these that are mapped to the same thing. And really, what are we asking about? We're asking about, given that F is constant, that it's mapped to 0, we're asking about the set of X that what?
F and G agree on.
F and G agree, and we know what F does, maps everything to 0. So we're just asking for the subset of X that G maps to 0, right? Which are precisely what Jeff mentioned, A and C. Right? It's just the subset of X that is mapped in the way that A maps things, which is to 0. The subset of X is mapped to 0. What if we took the equalizer? I've got to restrain myself because you can't spend all time. This is too much fun. What if F and G are the same? What if they both look exactly like this? So F and G both map A and B to 0 and C to 1. What's the equalizer of those two functions?
Capital X.
Capital X. It's the entirety of capital X, right? So it's A, B, C. So here, this is for the very special case where F equals G. It's the equalizer. It's the subset of this for which these are equalized. F and G. Are we comfortable with that?
In that case, little e would be the identity on X.
Little e is the identity on it. So, yeah, that's right. That's excellent. Yes. Here, what would little e look like? There's a little e here that goes from, it's not a C, it's a little e that goes from this. What does it look like here? This monomorphism. Well, it's an injective map, meaning there's no clashes, right? Because it's a monomorphism. So all it does is map this to this and this to this, right? Hmm? What does it look like here? It just looks like this. Right. These are just other names for these things. So, direct map over. Are we okay with that? If there were, mapped to the same thing, you couldn't say that there are other names, but here you could say there are other names, right? Because there's no, each one is on a one-to-one basis. If you do one, it maps to a single one here. Are we okay with that? So this is the equalizer. We haven't used this that much in Cephl to this point, but it's an extraordinarily useful construct. It's like a really useful gadget, I gotta say. And you can do it in a vast class of categories. You could use the equalizer. It's a limit construction, so it requires a category where you can take, you want a category where you could take limits typically. Maybe it's possible. I think I should know that, but I think if you have an equalizer, you can have monomorphisms and vice versa. I think there may be some categories which have equalizers which don't have certain other limits, for example. Okay.
Pullback, this alternative to pullback. Doesn't pullback filter some of them?
That's right. So Mehdi is saying that this is reminiscent of pullback. Yeah, I think that might be true. Hold that thought. I'd like to discuss it in office hours. It's really quite interesting.